The dynamic system that we are looking at is a small airplane, a Cessna 152, along with a pilot. The total mass of the system is about 1,500 pounds. This is a continuous system in the short periods that we record data, because no significant mass of fuel was lost.
The inputs to the system are the deflections of several controls by the pilot. These controls are the yoke, which inputs a desired roll and pitch of the aircraft, and the rudder pedals, which inputs a desired yaw, and finally the throttle, which inputs a desired thrust the engine will produce. The deflection of the controls mechanically command a deflection of the corresponding control surface on the exterior of the plane. Roll is controlled with aileron on the wings, pitch is controlled with the horizontal elevator on the tail, and yaw is controlled with the vertical control surface on the tail known as the rudder. The outputs of the system are the rotational and translational movement of the vehicle, which are measured and displayed on several instruments for the pilot to read. These instruments include an altimeter, a magnetic compass, an airspeed indicator, a ball slip indicator, as well as a couple gyroscopic instruments for non-visual conditions. The pilot also uses her surroundings to know where the plane is by simply looking out the window and her inner ear to sense any rotational movement.
What is actually being measured by the system is the ambient air pressure to find airspeed and altitude, the magnetic field produced by the Earth to display the aircraft's heading, and the direction of gravity, displayed as coordination and the ball slip indicator, and also felt by the pilot to detect changes in attitude.
At the beginning of the track, the heading is changed by the pilot by inputting a large deflection of the yoke to command a roll, and the pilot makes smaller and smaller changes based on the error, in this case the difference between the aircraft's current heading and the desired heading, which is displayed and fed back to the pilot via the magnetic compass. When the altitude was being changed, throttle was opened by the pilot to increase thrust and climb, and the error from the desired altitude, read from the altimeter, became smaller and smaller. The input by the pilot was reduced by smaller and smaller amounts to finally reach that altitude.
The control law, based on the data we collected, looks like a PID controller, as can be seen on this graph of altitude versus time, when we flew on a constant heading while decreasing altitude to the desired one. The coordinate frames are the body fixed frame, which is fixed to the aircraft with the origin at the center of gravity and the z-axis pointing down, and the inertial frame, fixed to the Earth with x and y axes synonymous to latitude and longitude, and the z-axis being height above the ground. Our data was collected in reference to the inertial frame, but some of the measured outputs are in reference to the body frame, such as roll rate. Well, I don't